So in this video, we're going to be talking about Kafka and what makes it so special in comparison to traditional message queue systems. So in order to talk about what makes Kafka special, we have to first talk about traditional message queue systems, what they're used for, and how they work. So with any type of message queue, we have a number of producers that can insert messages into the queue, and we have a number of consumers that will consume messages from the queue. The producers and consumers can both add or remove from the queue at their own pace, and the queue will hold any messages that haven't been consumed yet in the queue. This is really useful for asynchronous services, meaning that we can connect multiple microservices together. We can have them communicate at their own pace. It's also useful for event dispatch, so we can place events in the queue, and consumers of those events can read those events. And it's also useful for real-time communication, where we want to have messages that get sent, and then those messages are received by our clients in real time. Pretty much any time we have two services that we want to decouple and receive messages at their own pace instead of synchronously, message queues are going to be really useful. So with a traditional message queue system, if we have multiple consumers connected to our queue, each message will only be delivered to exactly one consumer. So if our producer puts 3 messages in the queue and we have 3 consumers, one message will go to the first consumer, one to the second, and the third will go to the third. So when a message is delivered by a producer, it'll get inserted into the queue. And then when a consumer consumes that message, it'll actually get removed from the queue. This means that a message can only be delivered once because once it's delivered, it gets removed from the queue. One interesting thing that we can do with traditional message queues is add in an exchange which can route these messages to multiple different queues. So for example, this exchange is configured such that the first message gets routed to both of these two queues, and the next 2 messages only get routed to the second queue. We can have different consumers consuming from these different queues, and each one will receive different types of messages. Using a hierarchy of exchanges and queues can enable super complex routing of messages between producers and consumers. There's endless possibilities of how you can route messages between different services using this architecture. So now that we've briefly covered traditional message queues, let's take a look at how Kafka works and what makes it a little bit different. If we have a producer that sends 3 messages into our queue, all 3 of those messages will actually get delivered to each one of our consumers. So in this case, each one of our 3 consumers is each receiving all 3 of the messages that were placed into our queue. Messages simply keep getting added into the queue, and they never get removed after they're delivered. That small detail is the root of almost everything that makes Kafka different. So if we're not removing messages from our queue, we have to have some other method of determining which messages a client has already received so we don't send them twice to the same consumer. So to do this, each consumer is given an offset. So to start, our offset is at the end of the queue, and our producer can add a message into the queue, and it'll sit in that queue. Once a consumer consumes that message, again, it doesn't get deleted from the queue. It'll simply get sent to the consumer, and the offset will update to be after that message. If this consumer pulled for updates again, it would see that there was nothing after this offset, so it wouldn't receive any new messages. Our producer can then add a second item into the queue, and it will sit at the end of the queue. If our first consumer polls again, it will receive that new message and update its offset accordingly. And if our second consumer polls, remember its offset was at the beginning of the queue, it will actually receive both of these messages and update its offset to be at the end. So again, we can see that both of these messages were delivered to both consumers. And because of this small detail, we can actually enable a ton of really interesting performance optimizations within Kafka. So the most obvious difference here is that when we're adding to the end of the queue, we're always writing to our disk sequentially. If you think about a hard disk, there's a physical head that has to move across the disk when we write to different areas. So if we're always writing into a specific region of the disk, one byte after another, our disk doesn't have to move very much. This is what makes sequential disk access much faster than random disk access. If we're removing elements from our queue, we're going to have to write from different areas of our queue depending on which items have been deleted and how many entries are remaining in the queue. However, if we have this log structure and we're always appending to the end, we're always writing sequentially. Now, when we're reading items from our queue, our disk doesn't even have to be involved in most cases. Reading from the queue can simply be done from the operating system's page cache. This is because whenever we write data onto the disk, our operating system will cache that data in case we need to access it later. So the last few entries that have been written into our queue will always be sitting in our operating system's page cache by default. When we want to read data, Kafka doesn't have to do anything special. All it has to do is go out and read from this page cache, and that'll always have the data that we need accessible in memory. So this very creative and very simple use of resources allows Kafka to really effectively take advantage of things that are built into our operating system and can significantly decrease overhead. This is what allows Kafka to scale to millions of events per second. So to wrap up, let's take a look at when we'd want to use Kafka and when we'd want to use a more traditional message queue system. We want to use Kafka when we have an extremely high throughput and we need to have that really fast throughput to be able to handle our load. Kafka is also good for when we want replay. So for example, if a client connects, they should be able to get all of the items that have been placed in the queue instead of just receiving new updates. Kafka also has data retention, so we can analyze that log after the fact if we want to look at something that has happened in the past. And finally, Kafka is good for situations where we want to fan out instead of sending messages to a single consumer. A good example of this would be an event dispatch system where we have a number of different services that are all listening to events, and any event that gets placed in the queue needs to be read by multiple systems at once. Traditional queues, on the other hand, still have their place and are very good for when we want complex message routing. Remember, we were able to have that system of exchanges and multiple queues, so we could effectively route messages between different consumers. Traditional queues are great for when we have messages that are intended for one or a fixed set of consumers, because messages are deleted from the queue once they're delivered and won't be delivered to multiple consumers. And finally, traditional queues are good when we have moderate data volumes and we don't need to have millions of events per second. Traditional queues are still very fast and they can be scaled even more through partitioning, but they'll never reach the same amount of scale that systems like Kafka can. If you enjoyed this video, you can find more content like this on interviewpen.com. We have tons of more in-depth system design and data structures and algorithms content for any skill level, along with a full coding environment and an AI teaching assistant. You can also join our Discord, where we're always available to answer any questions you might have. If you or a friend wants to master the fundamentals of software engineering, check us out at interviewpen.com.